pointed out to me that some solutions are coming in looking very alike. And I don't mind collaborating on these problems, but when you write them up, it's got to be in your own words and your own work. So please make sure. As I say, I don't mind you discussing problems with one another and coming to solutions, but then it's got to be written your way. Okay, so last time I wrote a theorem that covered the basic convergence of the power series. So I want to prove that this morning. So first of all, we need the fact that there is a radius of convergence, and that the set on which it converges should be symmetric interval. So let's consider sigma an x to the n from 0 to infinity, and suppose it converges at some specific point x naught. Then that means that the series sigma an x naught to the n converges and when you have a convergent series will have at least bounded coefficients. Because if we look at an individual term, an x 0 to the n, that is the partial sum from 0 to n minus the partial sum from 0 to n minus 1, ak x to k, ak x naught to k. So if the partial sums are converging, then their differences are tending to 0. So this goes to 0 as n goes to infinity. So the individual terms in the series must be going to 0, and that means that they must be bounded. So therefore, there exists capital M so that the absolute value of an x 0 to the n is less than or equal to m for all values of n.
Is the capital N dependent on the n, or is it universal over all?
Oh, which, the capital M?
Yes.
Okay, once we have that the sequence goes to 0, that means beyond a certain point they're all less than, say, 1 in absolute value. You only have a finite number of terms that you haven't considered yet. So there will be a bound for that too.
Okay.
and put the two together and get an absolute bound that works for every term in the series. Okay, so let us fix an x with the absolute value of x less than the absolute value of x naught. Then we're going to prove absolute convergence of the series, sigma absolute value an x to the n can be written this way. So multiplying and dividing by x0 to the n, I can write it that way. And now the first set of terms are bounded by m. So this is less than or equal to the sum from n equals 0 to infinity, capital M times the absolute value of x over x0 to n. Now, this ratio is less than 1. So this is a multiple of a geometric series where the common ratio is less than 1. So it converges since the absolute value of x over x0 is less than 1. And therefore, sigma an x to the n converges when the absolute value of x is less than the absolute value of x0. So to sum up, if you can find a single point where it converges, then you can actually find an interval on which it converges. Anything less than this number. And if you think about it for a moment, this means that if we let capital R be equal to the supremum of the absolute value of numbers x0 such that sigma an x0 to the n converges, then sigma an x to the n converges on the interval negative r to r, and if r is finite, it diverges on the intervals minus infinity to minus r and r to infinity.
Should the first interval negative r, should it close?
No, we never quite know anything about the endpoints. Okay? Basically because the supremum might not be attained. I wrote down some examples last time to show that all the possibilities of including none, both, or one of the endpoints could occur. And R is called the radius of convergence. want that a power series converges uniformly inside its radius of convergence. So suppose now that we take little r strictly less than capital R. So we've moved in a little bit from the radius of convergence. So there is a point x0 so that in absolute value it lies strictly between R and capital R, and sigma an x0 to the n converges. Now, the estimate that we got before using absolute value an x0 to the n less than or equal to m, we get that the sum k equals 1 to m plus 1 of the absolute values an x to the n, or ak x to the k, is bounded we'll just do the same trick as before. But now, if we're in the interval minus r to r, this is at most the sum k equals m plus 1 to n, m absolute value r of x0 to the k, as long as the absolute value of x is less than or equal to r. The point is that this is a constant, or a series of constants.
Should it be capital
Well, that would also be true.
Aren't you assuming x is greater than little r?
No,
0 is great.
little x in absolute value is going to be less than or equal to little r. So what we're doing here is we have the radius of convergence minus r to r, and then we're coming in a little bit, and we're looking at minus r to r, and because the radius of convergence is capital R, there must be some point x0 in there at which the series converges. So I'm trying to get uniform convergence on negative r to r. Now this series here is part of a geometric series. So this is at most now the sum from m plus 1 to infinity, m times the absolute value of r over x0 to the kth power. And that is a geometric series, so we can sum it. And this is m times the absolute value r over x0 to the m plus 1 divided by 1 minus r over x0 at no power. And the point is that as m increases, little m increases, that goes to 0 without reference to the particular x that we're talking about, as long as x is less than root to r. So this goes to 0 as little m goes to infinity. And therefore, on the closed interval negative r to r, partial sums converge uniformly, because we have an estimate on the difference that does not involve x. And therefore, sigma an x to the n converges uniformly on this restricted interval negative small r to small r. So as long as you come in a little amount from the radius of convergence, you will get uniform convergence of the series on that restricted interval. And that's for any little r less than capital R. In general, you won't get uniform convergence on minus capital R and capital R. So what this proves is that any power series will converge uniformly on one of these restricted intervals inside the radius of convergence. Now, we wanted to also show that the differentiated and integrated series have the same property. So, suppose now that sigma an x to the n has radius of convergence capital R, and consider the differentiated series nx to the n minus 1. I want to show that it has the same radius of convergence.
Do you need to toss an a in minus 1?
Yes, I need an an. Okay, so if the radius of the first one is capital R, let's choose little r less than capital R. let's let RD be the radius of convergence of the differentiated series. Okay, then sigma an r to the n converges because we're inside the radius of convergence for the first series. And just as before, there exists a capital M so that absolute value an r to the n is less than or equal to n. Now let's fix an x so that the absolute value of x is less than little r. So I'm going to come in a little bit more. So let's have a look at the differentiated series and let's estimate that. To prove convergence, a stronger thing is to prove absolute convergence. So let's have a look at the series n x to the n minus 1 from 1 to infinity. This is then the sum from 1 to infinity, the absolute value of n r to the n, and then I have to multiply by x to the n minus 1 absolute value over r to the n. And so this is less than or equal to the sum from 1 to infinity. I have this n. The an r to the n's I will estimate by that constant capital M. And then I'll take out 1r and put it underneath. And then multiply by absolute value x to the n minus 1 over r n minus 1. Now, this last term, x to the n minus 1 over r to the n minus 1, that's the n minus first power of a number that's less than 1 in absolute value. So we can apply the ratio test to this. Use the ratio test. When we look at the n plus first term, that's n plus 1 m over r times the absolute value of x to the n over r to the n divided by the nth term And that cancels down to n plus 1 over n times the absolute value of x over r. And as n goes to infinity, that m plus 1 over n goes to 1, and we're left with x over r less than 1 as n goes to infinity. So the ratio test tells us that that series converges. So, therefore, sigma absolute value n an x to n minus 1 converges for absolute value of x less than little r. So that tells us that the radius of convergence for the differentiated series must be at least little r. And since little r less than capital R was arbitrary, we get that the radius of convergence for the differentiated series has to be at least the radius of convergence for the original series. On the other hand, if I take any r less than the radius of convergence for the differentiated series, then as we've already seen, sigma absolute value n an x to the n minus 1 from 1 to infinity and that should be an r in there. Converges. But now the original series is at most the first term, which is a0 in absolute value, plus the sum from 1 to infinity. Now I can only make it larger by putting an n in. And I'll write the r to the n as r to the n minus 1 times r. But because I'm within the radius of convergence for the differentiated series, this infinite sum converges. So it converges since r is less than rd. So for any number less than r sub d, I get convergence of the original series, and that tells me that the radius of convergence for the original series must be at least rd. Therefore, r is greater than or equal to rd. series and the differentiated series have the same radius of convergence. Now what about the integrated series? Well, we've essentially done it already. If we apply this to the series sigma an x to the n plus 1 over n plus 1, which is the integrated series, its differentiated series is sigma an x to the n. So we already have a result that says if you have a series, it and its differentiated series have the same radius of convergence. So I've just applied that now to the integrated series. It says the integrated series and the original series, which is now the differentiated one of this, have the same radius of convergence. So therefore, sigma an x to the m plus 1 over m plus 1 and sigma an x to the n have the same radius of convergence. Finally, we want to show that the derivative of the original series is the differentiated series. In other words, differentiation term by term is allowed. So let R be the common radius of convergence so let f of x be the sum sigma an x to the n, which is defined for the absolute value of x less than r, and g of x is the sum of the differentiated series n an x to the n minus 1 for absolute value of x less than r. What I want to show is that f prime is equal to g. So let us fix an x with absolute value of x less than r, and choose small r so that absolute value of x is less than small r is less than capital R. So there's room to come in just a little bit from the radius of convergence. From what we've already done, on the closed interval minus r to r, both series converge uniformly. But now we've already had a theorem that deals with this situation. By theorem 2.3, if we had a series of functions and a series of differentiated functions, what we needed to prove that we could differentiate term by term was convergence of the derivatives uniformly, and the original series should converge at some point, when in fact we have it converging everywhere. So that was theorem 2.3. Theorem 2.3, f prime at that point x is equal to g of x. And that was an arbitrary point whose absolute value was strictly less than the radius of convergence. So then this holds. For all x in the open interval minus r to r. So things are as nice as they can be for power series. Differentiated and integrated series have the same radius of convergence. All of them converge absolutely on any, and uniformly on any smaller interval than minus capital R to capital R. And we are allowed to differentiate term by term. So the original series defines a function, and it's differentiable, and its derivative is what you get by differentiating term by term. So this is an ideal situation. You couldn't hope for more than this. Now, I mentioned that we're aiming for a specific series, and we want to prove various convergence results about it that we're going to find useful. And one problem that comes up, you can always prove things about power series on the open interval for the radius of convergence, but it can be quite hard to prove things about the endpoints. So I want a theorem that deals with an endpoint condition under a specific hypothesis. So let me state that theorem. I think we might just have time to do it today. So let f of x be a continuous function on the closed interval -1, 1. Let sigma an x to the n be a power series with radius of convergence 1, and such that all the ANs are non-negative for n beyond certain point. So we don't care about the first finite number, but beyond that, all the coefficients should be non-negative. Suppose that the sum of the series is actually equal to f of x in the open interval negative 1, 1. So this power series represents the given continuous function on an open interval up to its radius of convergence. Then the conclusion is that the sum from 0 to infinity, an x to the n, converges uniformly to the function f of x on the closed interval, negative 1, 1. So not only do we get convergence at the endpoints, but then we get uniform convergence to the function. So I'm not going to prove this in the next minute. So I think we should stop there today. Let me just say that it's normally quite a difficult problem to decide convergence at the endpoints. Even if you can work out the radius of convergence easily, it might be quite difficult to see what's going on at negative 1 and 1. But the hypothesis that it's already converging to a continuous function, and the fact that all the coefficients are essentially non-negative, as long as you go far enough out, that will suffice to handle the endpoints. Okay, so let's stop there. Is there any more